Mixtures of gases. Many gases are actually mixtures of different gases. Like air. Air is a mixture. These are the gases that are present in air. Air is mostly nitrogen, 78%, 21% oxygen, 0.9% argon, and then a little bit of carbon dioxide. And then all the other gases are in there as even smaller amounts, less than 0.04%. So we usually don't even talk about them. When it talks about dry air, that means air that does not have water vapor in it. We usually refer to that as humidity. So no humidity in the air, because like in Iowa in the summer, like the day we got married, it was 95 degrees and 95% humidity, right? In Iowa, Ames, Iowa. And it was like a sauna, right? There's a lot of water in the air, but that's going to be highly dependent on the temperature. And so it's really hard to think about the amount of water in air because that's going to change a lot. These gases are going to stay relatively constant in terms of their relative amounts. So we can treat a gas mixture as a single gas many times because the number of particles is what varies with the pressure, the volume, and the temperature. And so what exactly the gas is, whether it's 2 or 3 gases or a single gas, doesn't matter. But then sometimes we do need to know, well, what about this one particular gas? So we can calculate the total number of molecules of air, even though there are different molecules, because the gases behave independently. But sometimes we want to look at them independently. So if we look at the individual gases, what we find is that the pressure of a single gas, the single gas exerts a pressure on its container as if it was the only gas in the container. It's like it's in complete denial that there are any other gases in there. It's just going to do what it does regardless of what else is in there. We can kind of draw an analogy with mass. If you think about a big cardboard box, and you put 4 blue balls in the box, and each ball weighs 1 pound. So we've got 4 balls, 4 pounds, right? If I put a red ball in the box, does that change how much the blue balls weigh? No, it doesn't. The blue balls are sitting there having the same mass whether or not the red ball is in there. That's the way gases are. It doesn't matter if there are other gases in there. So the pressure of the single gas is called a partial pressure. Just like in that box of balls, the blue balls would have a weight, a mass, but the red ball in there is also going to contribute to the total mass of the box. So we have the mass from the blue balls and we have the mass from the red ball, and they add up together. That's how pressures work with gases. So each gas is going to exert its own pressure, and we can calculate what that pressure would be from the ideal gas law. So we've taken the ideal gas law and we've rearranged it, and it's written a little bit funny here for a reason, but the pressure from gas N is equal to the number of moles of that gas times RT over V. Dalton's law of partial pressures tells us that you add up all the partial pressures, and that's going to equal the total pressure. Just like in a box of balls, if you add up all the mass of the blue balls and the mass of the red balls and the mass of the green balls, that's going to give you the total mass in that container. And this is the same Dalton of Dalton's atomic theory. So we say that P total is the total pressure, and this is PA, PB, PC. These are the individual gases. So gas A, gas B, gas C. So the total pressure equals the sum of these partial pressures. PA, the partial pressure from A, is going to equal the moles of A times RT over V. We saw that up here, right? Everybody was okay with that? We're just going to change the n's here to A, B, and C. So the partial pressure from B is the moles of B times RT over V. These gases are in the same container, so the temperature and the volume are the same. The ideal gas constant is a constant, and so it's always the same. And here's the pressure from C, the number of moles times RT over V. Well, we can factor out this RT over V, and so the total pressure is equal to the sum of the moles of gas times RT over V. So the total pressure, I should bring that down. The total pressure equals the total number of moles times RT over V. So if we take the partial pressure of gas A, which is equal to the moles of A times RT over V, and we divide that by the total pressure, which is the total number of moles times RT over V, RT over V cancel out. The partial pressure of A divided by the total pressure is equal to the number of moles of A divided by the total number of moles. This is called the mole fraction. It's like a percentage that's not multiplied by 100. Yes?
And that's just to figure out how much of PA there is in total?
We're going for this guy down here. It's a relationship between the partial pressure of a gas, the total pressure, and the mole fraction of that gas. So if I'm losing you on this whole derivation thing, just hang on, and we'll get to the punchlines right down there. So chi A, chi is what we use to represent mole fraction. That's the moles of the one part that we're interested in divided by the total. So we said percentages were the part divided by the whole times 100. This is the part divided by the whole. Don't multiply by 100. It's a fraction instead of a percentage. So then we've got this guy is equal to this. So that's just copied down here. And then we're just rearranging this. So we get, well, we just get down here. So this is the bottom line. If the derivation made no sense to you, just memorize that. You'll kind of need this guy too. The pressure of a gas, a single gas in a component, is equal to its mole fraction times the total pressure. If half the molecules are oxygen, then oxygen is going to exert half of the pressure. That kind of makes sense, doesn't it? If a quarter of the molecules are oxygen, then oxygen exerts 1/4 of the pressure. I can. It's okay.
So for the last part, or the one directly above it, where you have chi A times P total, what happens to the PA? Is that just...
PA equals,
okay.
So what we did here is we took this P total and we multiplied both sides. So, so if we multiply by P total on both sides, then the P total cancels out over here. And so that's how they're getting this. PA, here's my pointer. PA equals this mole fraction, Na over N total, times P total, which is chi A P total. And there it's just written out nicer. The partial pressure of a component, a single gas in a mixture, is its mole fraction times the total pressure. So the mole fraction is related to a percentage. The mole fraction is just the percentage divided by 100. So if we look at air, air was 78% nitrogen. Then the mole fraction is 0.78. So the mole fraction of nitrogen is the 78% divided by 100. So the mole fraction is 0.78. Fractions, as we're using them here, have to be less than 1. So here we've got the mole fraction of nitrogen times the total pressure of air at sea level. And so we find out that the partial pressure of nitrogen is 0.78 atmospheres. To prevent the presence of air, noble gases are placed over highly reactive chemicals to act as inert blanketing gases. So there are some chemicals that will react with gases in the air. And so you can't just put them in a jar. You have to cover them with something. And if you don't want to cover them with some sort of a liquid, you can cover them with a noble gas. The noble gases don't react with anything, and so it'll all just sit there nicely and behave itself. So the chemical engineer places a mixture of noble gases consisting of 5.5 grams of helium, 15.0 grams of neon, and 35.0 grams of krypton in a piston cylinder assembly at STP. Calculate the partial pressure of each gas. Well, let's think about this. We have 3 different gases in here. So what do we know about mixtures of gases? We learned 2 equations. One of them is Dalton's law of partial pressures, which says that the total pressure of this thing is going to equal the partial pressure from the helium, plus the partial pressure from the neon, plus the partial pressure from the krypton. And what was the other equation that we learned?
Partial pressure equals chi p total.
Yeah, the partial pressure of a gas, I'm going to write it for helium, equals the mole fraction of that gas times the total pressure. So those are the 2 equations that we have for mixtures of gases. Well, these are the things we're trying to find, right? The partial pressure of each gas. Do we know what the total pressure is?
It's
At STP, what's standard pressure? 1 atmosphere. So we know that this is equal to 1 atmosphere. But we've got 3 unknowns there. This equation isn't going to help us. Then we've got this one. This is what we're trying to find, the partial pressure. We know what the total pressure is. Could we figure out what the mole fraction is? Do we have information that could let us figure that out? We've got masses, right? If I have the mass of helium, could I figure out how many moles of helium I have? Yeah, and I could figure out the moles of neon and the moles of krypton, and I could add those together and get the total number of moles. I could calculate the mole fraction. It's a lot of work. Yeah. I never claimed that chemistry is not tedious at times. Okay, so let's do it. For helium, we have 5 grams. And we want to find out how many moles that is. So we need to divide by the molar mass of helium, which is 4.003 grams. 5.5 divided by 4.003, 1.37. That's my 3rd significant figure. And I'm going to carry 2 more. I've got 396. That's going to round up to 40 moles of helium. And then neon. So I've got 15 grams of neon. And 1 mole of neon weighs 20.18 grams. So I've got 15 divided by 20.18. 0.743. Here's my 3 sig figs. 31 moles of neon. And then I've got my krypton, 35 grams. Does this look like a problem that you want to just do in your head without writing anything down?
No.
No, I wouldn't. 83.80, not if I wanted to get it correct. And if you don't want to get it correct, then why bother doing it at all? 35 divided by 83.8. 0.41766 moles of krypton. So, to find mole fractions, because that's what we need. We know what PT is. We need the mole fraction of each of these guys. We'll multiply it by PT, and that'll give us the partial pressure. To find the mole fraction, we take the number of moles of the gas we're looking at and divide by the total number of moles. So the total number of moles, let's call that N total, is going to be the sum of these, right? 1.374 plus 0.74331 plus 0.41766. 2.53497 is what my calculator tells me. How many significant figures does that result have? 3. We're adding. We've got 2 decimal places here, 3 decimal places, 3 decimal places. Our answer should have 2 decimal places. I'm not going to round it off yet, but I'm going to just keep track of it because it's easier to keep track as you go along. So the mole fraction for helium is going to be 1.3740 moles divided by 2.53497 moles.
So the letters is what makes it more confusing. It's just fractions. Right?
It's just fractions. Yeah, it's just fractions. It's the part that you're interested in divided by the whole thing. So this is 0.54202. There's no unit on that because the moles cancel. So it's close to half helium, right? If it was exactly half, this mole fraction would be 0.5. If we wanted to know what percentage helium it would be this times 100, 54.2% helium. And so we can get the mole fraction for neon. That's going to be 0.74331 moles divided by 2.53497 moles. I thought this was tedious yesterday when I did it, and now I get to do the same stupid problem again. I'm supposed to pretend that I'm excited about it. 29322. So that's the mole fraction for neon. There's 2 ways we could calculate the mole fraction for krypton. We could subtract both of these from 1, and that's going to give us the mole fraction of krypton.
Just real quick. So 0.54202 is the pressure helium, right?
It's the mole fraction, and because the pressure is 1, it is also the pressure.
If the pressure was different, it would be different.
Right.
I understand.
Yeah. So this is the mole fraction. So let's just continue on with that one. And so to calculate the partial pressure of helium, we're going to take the mole fraction times the total pressure. The total pressure is 1 atmosphere. And since it says it's at STP, I would assume that the STP part is exact or more exact than the other measurements. And so I'm going to say that this is 0.542 atmospheres. The helium is a little over half the number of moles. It's a little over half the total pressure. And so after you do that, you say, oh, well, it ends up being the same. And so then I would be cool with you just saying, okay, well, then the pressure of neon is 0.293 atmospheres because it's the mole fraction times 1. And so for krypton, we can calculate the mole fraction by taking 1 and subtracting these two numbers, or we can do it the same way. Do it whichever way makes more sense to you. 0.41766 moles over 2.53497 moles.
So is this what we'll be doing today, but we'll just be doing it with one, because we're doing an unknown?
We're not doing this partial pressure or mole fraction business because we're using a single gas. So it'll be like the previous examples where we were calculating molar mass. So that's the mole fraction, and then that's going to also be equal to the partial pressure because this is at 1 atmosphere. So if we take those pressures, 0.542 plus 0.293 plus 0.165, they add up to 1.001. That last digit not being exactly 1 is just a reflection of this being data with uncertainty. Any questions? Here's another one. A sample of hydrogen gas is mixed with water vapor. So again, gas mixture. Here we've got two gases, water in the gas state and hydrogen. The mixture has a total pressure of 755 torr, and the water vapor has a partial pressure of 24 torr. What amount in moles of hydrogen gas is contained in 1.55 liters of this mixture at 298 Kelvin? Well, let's write the numbers down. So the total pressure, I'm going to call that P sub T for total. P total is 755 torr. And the water vapor has a partial pressure of 24 torr. Okay, let's think about just the pressures here. We have two gases. So Dalton's law of partial pressures tells us that the total pressure is going to equal the pressure of the partial pressures of the two gases added together, the hydrogen and the water. We know the pressure of the total mixture, and we know the pressure of the water. We can find the pressure of hydrogen. And this is one of those things where the calculation is so easy that people lose their minds and can't do it. It's just the total pressure minus the pressure of the water. So it's 755 minus 24. So 731 torr. I did the math in my head. I don't recommend that you do that on an exam, though. You'd be surprised even on labs how many times people subtract and get it wrong. So this is the pressure of just the hydrogen gas. And then what else are they giving us here? 1.55 liters. That's a volume, right? And 298 Kelvin is a temperature. So I have volume, I have temperature, I have pressure, and they're asking for moles, N. So I'm going to use the ideal gas law again. N equals PV over RT. all the examples end up using that same equation.
Which is nice.
It is nice, right? So we need to convert torr to atmospheres. So we're dividing by 760 torr. 731 divided by 760. Most of our problems that we're going to see, the pressure in atmospheres is going to be fairly close to 1. Because if you get up to 2, 3, 4 atmospheres of pressure, that's a lot of pressure. And unless you have a very specialized container, it's going to explode. So there's our pressure in atmospheres. Okay, so plug the numbers in. 1.55 liters. Now, yeah, let's keep that in order to avoid confusion. The pressure was first. Not that it matters, but I don't want to add to confusion. 96184 atmospheres. Volume, 1.55 liters. What's the value of R? 0.08206 liter atmospheres per mole Kelvin. We end up using it so much that we memorize it even if we don't realize it. And then 298 Kelvin.
Now, if we were to, like, if we were writing this out on a test, would you mark us wrong if we didn't put, like, ATM, L, like, all that in the equation?
Like if you left the units out?
Yeah.
I probably would not mark you off, but I would discourage you from doing that. I might write, show your units. So this comes out to be 0.06096, and so that rounds up to 610 moles of hydrogen gas. Any questions? You should always do significant figures.
So we're not really going to get into, like, exactly molar masses with this stuff, right?
Usually with mixtures of gases, we're not doing molar mass calculations, but it could happen. Deep sea diving. So when a diver breathes compressed air, you're getting an abnormally high partial pressure of oxygen. The partial pressure of oxygen at atmospheric pressure is 0.21. That's a great pressure for us. That's what our bodies are designed for. If you get to a higher pressure, then the pressure of the oxygen goes up as well. And then you get too much oxygen in your blood. The thing is, anything is toxic and too high of an amount. Did you know that water is the chemical that kills more people than anything else? Now, a lot of those people drowned, right? But the water is what killed them, right? Too much water will kill you. So let's ban water. We can't do that because you'll die without water too, right? Balance, moderation. So too much oxygen is bad as well. Too little oxygen is bad. There's a sweet spot in the middle. Too much oxygen, you get oxygen toxicity. You can actually die by breathing too much oxygen.
Just a little bit too much is kind of fun.
A little too much might be fun, but a lot too much isn't. Hypoxia is oxygen starvation, and basically you're going to suffocate even though you're breathing because there's just not enough oxygen. So you get too low and you get hypoxia. When you're breathing compressed air, you're also going to be breathing a higher level of nitrogen than your body is used to. And if you get nitrogen pressures above 4 atmosphere, you can experience nitrogen narcosis, also called rapture of the deep. The symptoms are similar to alcohol intoxication. Whoops. You might say, oh, well, that might be good, and then I could be drunk and I could still pass the breathalyzer test. Yeah, no. Yeah, you could die. So, you think about the guy at 30 meters, we talked about how each 10 meters you go down, you get one increased atmosphere of pressure. And so the total pressure on your tank needs to be 4 atmospheres, because otherwise you're not going to be able to inflate your lungs. So at 4 atmospheres, then the partial pressure of nitrogen is going to be 3.12 atmospheres, which is getting up close to this 4 atmospheres where you're going to be in trouble. If you're 30 meters below the surface of the water, you do not want to be in a drunken state, right? You don't want to be losing your judgment and your faculties. So to combat this, they use different mixtures of gas, and one of them is called heliox. It's a mixture of oxygen and helium. The helium would make your voice really high and squeaky, but nobody can hear you talk down there anyway. But the helium is not going to cause narcosis or anything like that, and so you can breathe elevated pressures and not get into trouble. So let's look at this example. A diver breathes a heliox mixture with an oxygen mole fraction of 0.050. What must the total pressure be for the partial pressure of oxygen to be 0.21 atmospheres? Well, let's think about this. The oxygen mole fraction. What symbol did we use for mole fraction? Chi, that funky big X. So chi O2, the mole fraction of oxygen is 0.050. And it says we want a partial pressure for oxygen to be 0.21. So that's the pressure of oxygen we want to be 0.21 atmospheres. And it's asking about the total pressure. So P total equals question mark. We don't know. Well, we can use that equation. The partial pressure of oxygen equals the mole fraction of oxygen times the total pressure. So we just need to rearrange. Divide both sides by the mole fraction. These guys cancel out. The total pressure is going to be the partial pressure of oxygen divided by its mole fraction. And we know both of those numbers. So 0.21 atmospheres divided by 0.050. Bless you. 4.2. So with this particular heliox mixture, if you're breathing this at a pressure of 4.2 atmospheres, then you're going to be okay. You're going to have a good level of oxygen. Any questions? Collecting gases. Gases are neat to work with because we can determine the number of moles by measuring pressure, volume, and temperature, but they're kind of difficult too because they don't just sit in the bottom of a beaker. You know, if they're not contained, they float away and they mix together too easily.
Can I see that last slide?
Yes, you can see that last slide again. So how do we collect gases? Let's look ahead at this picture. So here's a reaction that generates gas. So we mix zinc metal with hydrochloric acid. It generates hydrogen gas. And we want to measure how much hydrogen gas is given off, maybe the number of moles or the mass of it. How do we do that? Well, we have this reaction occur in a closed container. Here it's a test tube with a one-hole stopper in it. And we have a piece of glass tubing in the hole directing the gas down underwater and under this inverted beaker. When we started this experiment, this beaker was completely full of water. There was no air or anything in there. As the hydrogen bubbles through here, it comes to the end of the tube and it's going to go up. And so it's going to go up and get trapped in this inverted container. As it gets trapped up there, it's going to displace the water. Does that make sense? So we've got hydrogen in here, but we also have water because the water will begin to evaporate from the surface. The amount of water in the gas state above this liquid depends only on the temperature of this situation here. And so what we've got up here is a mixture of hydrogen and water. So now let's go back to the words.
How do you make that? How do you get the water in there if it's inverted and stuff?
How do you get that? That's a good
How do you
question.
make it?
Right. So there's different ways you can do that. If you're really fast, you can just flip it over. But usually what you do is you could use parafilm. If you're quick, you could use even something like a watch glass or your hand to cover the beaker as you flip it over and sink it under. Or you could do it, this is a shallow dish, but if you had a deep reservoir of water, you could actually just put the beaker underwater, tip it upside down, and lift it up. And it would be full. Then you'd need to hold it there. And that's something you can play around with in the sink at home, right? Take a cup upside down and lift it up, and the water stays in. And my kids had endless fun with stuff like that in the bathtub. And I refrained from explaining to them what was going on. Okay, so we get water vapor in there. This is called collecting over water. So we've got water vapor and the gas we're interested in. The partial pressure of the water vapor is called the vapor pressure, and that depends only on the temperature. And so we can measure the temperature and then just look up what the vapor pressure of the water is. And so that's convenient. We look it up in a table like this. This one gives 5-degree temperature increments. You can find other ones that are more specific. But for example, at 25 degrees, the vapor pressure of water is 23.78 millimeters of mercury. As you heat the gas up, it gets higher and higher until when you get to the boiling point of water, then the vapor pressure is equal to the atmospheric pressure. So there's the picture. Let's look at this example. A sample of acetylene is collected over water. So that collected over water tells us there's water vapor and acetylene. The total gas pressure is 738 torr. The volume is 523 milliliters. At the temperature of the gas, 23, the vapor pressure is 21 torr. Vapor pressure of water. How many grams of acetylene are collected? Well, let's write down these numbers. So it says the total pressure is 738 torr. The volume is 523 milliliters. The temperature is 23 degrees Celsius. Let's just convert that to Kelvin right away. 296. And the vapor pressure of water, so that's the partial pressure of water, at that temperature is 21 torr. So we want to know grams of acetylene. We have gases, so we're probably going to need the ideal gas law. The ideal gas law gives us moles, right? If we got moles of acetylene, could we figure out how many grams? Yeah, that'd be pretty easy. Okay, so we're looking for moles of acetylene. So here's that same equation again, the rearranged Pivnert. Pressure, volume, R, it's not a very good R, and temperature. What's important here is that the pressure that we use is the pressure of the gas that we're interested in. Otherwise, we're going to get the total number of molecules, including water, and we don't care about the water. So we don't want to use the total pressure, we want to use the pressure of the acetylene. So the partial pressure of the acetylene is the total pressure minus the water. So that's 738 minus 21, so 717 torr. What unit are we going to have to convert that to? Atmospheres. divided by 760. So 717 divided by 760, 0.94342 atmospheres. And our volume needs to be in liters. 523 milliliters is how many liters? 0.523. Because that's half of a liter. Okay, plug these in. Pressure, 0.94342 atmospheres. Times the volume, 0.523 liters, 0.08206 liter atmospheres per mole Kelvin, and temperature 296.15 Kelvin. So number of moles, 0.020303 moles. We're going to convert that to grams using the molar mass. Grams and moles. So 2 carbons times 12.01 plus 2 hydrogens times 1.008. Molar mass is 26.036. Times 0.020303. 0.529 grams. Any questions? There's like an infinite number of problems that could be asked.
So chapter 5's pretty simple if you know how to use that equation.
If you know how to use the gas laws, chapter 5 is pretty simple. If you're having trouble with the gas laws, if you don't have unit conversions down to easily convert between torr and atmospheres, if you're having trouble rearranging equations, you're going to have a rough time. Yeah?
What's the hardest question going to be about?
I don't know because I haven't written the exam yet.
You still haven't written it?
No, it's not. I don't have to give it until tomorrow at 1:30. It's like over 24 hours away.
Procrastination's like super bad, they say.
It works for me. It's worked really well so far. Here's another example. A common way to make hydrogen gas in the laboratory is to place a metal such as zinc in hydrochloric acid. That's what that illustration was of. The hydrochloric acid reacts with the metal to produce hydrogen gas, which is then collected over water. That's the whole backstory. Suppose a student carries out this reaction and collects a total of 154.4 milliliters of gas at a pressure of 742 millimeters of mercury and a temperature of 25 degrees Celsius. What mass of hydrogen gas in milligrams does the student collect? Same thing. Yeah. Lots of different words. We still have this collected over water. Now, a common mistake is that students would just take these numbers and plug them in to the equation and calculate moles and convert to milligrams. Can I use this pressure? No. That's the total pressure. The collected over water means I have a mixture of the gas I'm interested in and water vapor. This problem doesn't tell us what the vapor pressure of water is. We have to go look it up. Okay? You do not need to memorize this table. If you need it on this isn't on the exam on Thursday, but if you need it on an exam, I'd either give it to you in the problem or the table might be provided next to the periodic table or something, but you'd have to go look for it. So we go looking at the table. 25 was the temperature, right? 23.78 millimeters of mercury. So the vapor pressure of water is 23.78 millimeters of mercury. So we're getting a little more familiar with this. We look at this and we say, oh, well, this is the same old thing. I'm going to have N equals PV over RT. And so I need the pressure, but I need the pressure of the hydrogen. So I'm going to take that total pressure, 742, and I'm going to subtract the 23.78. $742 minus 23.78. 718.22 millimeters of mercury. I need to convert that, don't I? So times 1 atmosphere over 760 millimeters of mercury. Divide by 760. 0.94503 atmospheres. So I've got the pressure there. What's the volume in liters? 0.1544 liters. I'm fine with you doing that in your head, but I would like you to write it down here. I want to see the equation with the numbers plugged in.
So we can use the total volume for.
You're going to use the total volume, because the thing about gases is, we got 2 gases in there, but they both have the full volume. And that's a little hard to think about, but that's because there's so much space in between the particles that they can just intermingle like that. Solids and liquids can't do that. But you put 2 gases in a container, and it can have the same volume as each of the gases individually. So 1 liter plus 1 liter does not necessarily equal 2 liters for gases. Then we've got R, 0.08206 liter atmospheres. I should make a thing where I can just paste that in there. Use it so many times. What's the temperature? 298. I happen to know that 25 is 298. But we're taking the 25 plus 273.15, 298.15. Yes?
So what would an example be if we were not going to use the total volume?
There won't be an example where you don't use the total volume, because the volume of each gas is the total volume.
So would it be like, what's the partial volume or something?
No, it can't be,
Okay.
because that's one of the properties of gases. They expand to fill their container. You got 2 gases in there, they both expand to fill their containers. Okay, 0.95, sorry, 94. I actually typed it right and said it wrong. 94503. Is it Friday yet? Times 0.1544. It could be. 1.820. It's it's Friday somewhere. It's 5 o'clock somewhere. I don't think it's Friday somewhere.
I never said
It's Wednesday somewhere.
on planet Earth. There's an infinite universe.
An infinite universe.
We're stretching the sunlight.
Yeah, we're stretching it there. 596.
Like a gas.
Like a gas. Expands to fill the space available. It's like homework. Expands to fill the time you have.
It does.
This is moles.
Go to my donut, too.
So how do we get milligrams? Well, we'll go to grams first. How many grams per mole for hydrogen gas? 2.016, because it's H2. And then grams down here, milligrams on top. 1 milligram, 10 to the minus 3rd grams. times 2.016. Oops, that's wrong. 12? 12.0 milligrams. Those balances sound like cows, don't they? We have the self-calibrating balances over there, and they start mooing during class. Any questions?